Okay, everyone. Let's get going on our last lecture of the week. It is Friday again. I'm not quite sure how that happened. And today we're going to be talking about the implications of a summer sea ice-free Arctic. And you can't really see very well. Let me turn the lights a little bit further down. But this is a little picture showing what our Arctic Ocean would look like without its nice white sea ice covering. And this isn't necessarily science fiction. It's not necessarily something that is too distant from what we might expect. So this is the lecture that really inspired me to create this class in the first place, because we are seeing such dramatic changes in the sea ice extent. And in particular, I'm going to show you what happened in 2012. And I asked a whole bunch of ESS majors, let alone some of the people in my bigger classes, and no one knew about it. And it's just not reported. And this is a huge, huge fundamental change to our planet. And so I was like, I don't care. Okay, if Fox News or NBC or CNN isn't going to report this, then fine. I'm going to force you to listen to me instead. And so what we'll do is we'll talk about sea ice today, and certainly the implications of what this disappearance means to us. So, first of all, I have a question for you, which is, does melting sea ice contribute to sea level rise? And if you've had my classes before, don't give the game away. Okay, a few more seconds. Right, let's take a look and see what we think as a class. We think there's a 60-40 split to yes, no. So, we started a little bit late because I was busy creating a mess at the front. I've managed to dye lots of myself pink. So I have a little experiment for us, real science, and it's difficult for the people at the back, and I'm really sorry about that. But I have a beaker here. It has water in it, and it has a layer of sea ice, my fake sea ice in here, okay? So what we're going to do is I've drawn a line marking where that water is, and we're going to see what happens over the course of our 50-minute lecture, okay? And for comparison, I have, this is where I was making a real mess, I have an equivalent where we have basically what's happening with land ice, right? Which is I have my nice ice piled on land, and it's gradually going to melt and drip into my ocean underneath. And again, it's about the same level as that black line, and so we're going to come back at the end of the class, and we're going to see what has happened to our sea level, okay? So I'm not going to give you the answer just yet. We're going to come back to it, and it's going to be the last question of the day. So, we want to monitor sea ice. We would like to know what's happening to it. It's one of the things that is really responsive to changing climate. And so what we would like to do is be able to get an idea of what's there, how it's changing, but also how those changes relate to what's happened in the past. And so first of all, if we want to measure sea ice, what do we want to measure? What would you want to measure? Perhaps density, perhaps. What would you care about more if you were a fisherman or something? How thick it is, that's a really good one, absolutely. So the thickness of the sea ice. So one of the things that we think about most frequently is just how broad an area does it cover. And so we definitely care about the sea ice extent. We want to think about how broad an area it covers. But what we also want to think about is the thickness of it. So if most of our Arctic is now covered by an ice layer that thick, that's very different from if it's covered by an ice layer a couple of meters thick. Okay? So we definitely want to measure both of those. So how do you think we monitor sea ice today? Satellites. Okay, that's always our answer right now, satellites. And we're going to talk in a couple of seconds about just how we go about doing that. But the question is, how could we sort of get an idea of how our sea ice has been changing before we had satellites? Because we've really only had those for the last sort of 40 years or so, and the particular satellite that measures volume for us, we've only had for the past 3 years. So actually, how do we get a record further back in time? Does anyone have any ideas? Ice cores? Perhaps on land, it gives you an idea of where the temperatures, what the temperatures on land have done. But we can't take ice cores of sea ice. It's just not that old. It's probably only a few years old at most. Sea level? We'll come back to that one. Any ideas? If you lived on Iceland, or anywhere pretty far north, and you were dependent on, say, the ocean for your food source, and how much fish you were catching perhaps, then you probably cared quite a lot about this. And so we can actually go back to sort of cultural records, and they will tell you sort of how often they could get out of harbour, and how far the sea ice came down and how sort of long it stuck around. So things like that can help us out. Other things like we can find specific chemicals that are released by that algae that grows in that sea ice. And so if we find that particular chemical in our sediments in our ocean, then we can probably say that the sea ice probably extended that far, although it's a little bit more of an uncertainty. Does anyone know, oh, well, I know you're all very young, but you should know what happened in the 60s that was particularly relevant to the Arctic Ocean, perhaps. Who were the US's main enemy? Russia. What did we call that particular time? The Cold War. Why? It's pretty cold up there, right? Because we think of Russia being like sideways on. Actually, the closest way to get to Russia from here is across the top, right? Okay. What do you think we had around in the Arctic Ocean during the 60s that might have cared if there was sea ice or not? Submarines. Okay, so we're going to have a look at our submarines in a second. It's really fun. Okay, so things like our shipping records, ocean temperature records, our ice core records, certain chemicals and sediment. These are how we can reconstruct and at least have a rough idea what sea ice might have been like in the past. And of course, today, our satellites are just amazing at helping us out with this over much larger areas. So one of the easiest ways of knowing what is there in terms of sea ice is just going out and measuring it. So we go out and we can make observations, and we can also sort of drill through and work out what depth there is. But obviously that is enormously time consuming. It's not exactly a friendly place to be, and we can't necessarily do that in a nice network all over the ocean. And so it's very, very important that we do this in places to test our satellite data to make sure it's actually telling us something that is vaguely realistic. So it's really helpful for that, but we're not going to get a big enough pattern just by direct measurements today, even these guys sort of having to cart their equipment around. But submarines are a really good way, and this was sort of information that was declassified relatively recently, because as submarines travel under the ice, first of all, they don't want to bump into the ice. The ice is pretty solid, and it could do damage to them, and so they're constantly scanning the bottom of the sea ice to look for these big keels where that sea ice has sort of come together and created greater thicknesses. But also, sea ice is really tough, and so if you want to surface and shoot your missiles at someone, you want to know how thick the ice is, because you can only do that through a certain thickness. And I have a really fun video to show you, because it's nuclear submarines. Why would we not want to see nuclear submarines? It's really fun. And so you can see just how tough it is to get a submarine through this sea ice. So the sound it makes is pretty spectacular as well. But that sea ice is pretty thick, and it's forming a quite solid lid on the ocean there. And you can see even that force of the submarine, the buoyancy of that submarine forcing its way up. You can see that in a second, it's going to hit the rest of the surface, and it's basically going to bounce. There it goes, and no further. Okay. So that sea ice is tough stuff. And so if those submarines were going to be able to break through that sea ice and launch missiles at anyone or get access to the open air, they needed to know how thick that ice was going to be. And so for a lot of the past few decades, these submarines have been measuring that thickness of the sea ice. And so once those records were released to us, it was a huge help in understanding especially how the volume of our sea ice has been changing. Because as I said, the satellite that we use to do that has really only been around for the last 3 years. So we really needed those records. It's also one of the reasons why we have a much better idea of what's going on in the Arctic compared to the Antarctic. Because in the Antarctic, we just don't have submarines zipping around under the ice down there as much. Okay? So fun stuff for today. So let's think more about satellites, because they're actually sort of the main way that we can study ice today, and we're learning enormous amounts about sea ice from this. And really, we have very good records of sea ice extent now, going back to maybe 1978, 79. And that's because we had our first sort of set of satellites that were put into orbit. And what these do is they passively measure. They don't beam energy at the Earth. They just receive what is being emitted. Remember, energy is always being emitted by the Earth because we're above 0 degrees Kelvin. We're above absolute zero. And the key thing is that our different surfaces, so for example, ocean water, salty first-year sea ice, or fresher, older sea ice, all of those emit slightly different spectrum of radiation. And so as our satellite flies over, it's detecting that radiation being emitted by those different surfaces, and so we can get a sense of what sort of the sea ice extent is around this area, which is really neat. And the nice thing about microwaves, especially in this sort of passive way, is that it can see through clouds. It doesn't care if there's clouds there, so it can see right down through those and get a sense of what's going on. Okay? But we have this extra cool satellite now called Christat II, because Christat I unfortunately blew up as it was being launched. And so it's got an active radar. So instead of being passive and just receiving things that are emitted by the Earth, now it's actively broadcasting radio waves down at the Earth's surface. And it receives back, basically it bounces that energy back up to the satellite. And so what we can do now is we can measure differences in height. So you can see in my right-hand diagram here that that satellite is broadcasting radio waves down, and depending on the height of the surface, it will sort of bounce back at a slightly different point. And what the satellite can do is it can detect those differences. And when we think about sea ice, why this is so helpful to us is if you have really, really thick sea ice, then more of it is going to be floating above the water. Does that make sense? If you've ever been in a swimming pool, hopefully this sort of makes sense, that the thicker there is underwater, the more is floating above. And this is something we call freeboard. Okay? So you can see this in my diagram here. I stole from the BBC News website, because they're very excited about this too. Our cryosat comes over the top. It beams this radio pulse down, receives it back. And what it's basically measuring is the difference in height between the sea ice surface and the ocean surface. And that is related to the thickness of the ice underneath. And so for the last 3 years, we're extremely excited because we now can get finally a really good sense of what's happening over the whole Arctic Ocean in terms of the volume of our sea ice, as well as just the extent. Okay? So it's very neat, and it can detect changes of like a couple of centimeters. It's really, really amazing. Okay. So what does our sea ice do? Now that we have these amazing observations, what does our seasonal sort of sea ice extent look like? So first of all, we have Antarctica over on the left-hand side, and you can see that in its sort of October time, which is the end of its winter, then you can see that we've got nearly 20 million square kilometers of ice around Antarctica. It's a really big continent. It's really cold down there. But look how much it loses. In the summer, it only maybe has sort of 3-4 million square kilometers. And you remember that in Antarctica, we just have this open water. It's a continent surrounded by ocean. And so when those winds blow that sea ice, it's really easy for that sea ice to be moved to warmer places where it can melt away. And so that's why in Antarctica especially, we don't tend to have that ice sitting around for that long, and so we see a really big change between the winter and the summer. If we look in contrast at the Arctic, we don't actually have as much sea ice in the winter or the end of the winter in the Arctic, but we also don't lose as much of it in the summer, or we haven't lost as much of it in the summer yet. And so you can see that here our cycle tends to go from maybe 14, 15 million square kilometers, so really occupying most of that Arctic basin and into the Atlantic and Pacific. And then at the end of the summer, we're down to maybe sort of 5 or so square kilometers. Okay? And those different colors there represent the most recent years. And you can see that there's a funny pattern going on. In Antarctica, there doesn't seem to be really that dramatic a change yet. And that's really true. We're not seeing huge differences in terms of the sea ice extent. But if you look at the Arctic, that dotted line, that black dotted line shows the average between 1972 and 2012. And you can see that in recent years, we are very much underneath that. And in fact, often if you look in successive decades, we're getting lower and lower and lower in the summer especially. Not so much in the winter, but the summer especially. So let's have a look at some of those things. So this is showing both of the Arctic and the Antarctic with their sort of minimum sea ice extent. Okay? So in blue we have the Antarctic. And remember we said there's less sea ice actually around Antarctica in the summer, even though it's a pretty big place. You can actually see that even though there's quite a bit of noise there, if anything, we've been growing a little bit of sea ice at the end of summer in Antarctica. And this is a really puzzling thing for a lot of us. And we're really interested in understanding why that's the case. Because definitely as we continue to look forward in time, we're really expecting to see a decrease much like we do in the northern hemisphere. But it might be things like wind patterns are changing slightly, which allows us to keep more of that ice than we have before. It's a really interesting idea and question. But if we look at the Arctic, in that September, that minimum of sea ice extent, you can see that compared to, say, 1980, we are really seeing a steady decline. There's no real argument about this. And it's not a trivial amount either. If we start off in 1980 with, say, between 7 and 8 million square kilometers, by 2012 we were down to less than 4 square kilometers. So it's a pretty dramatic change. And so I want to put that in context, because again, that's just, say, the last 30 years. What does that look like if we look, say, maybe at the last 1,000 years or 1,300 years? And so to do that, we have to use some of those different ways that we can reconstruct sea ice. So this isn't satellite data for the last 1,000 years, obviously. And so there are uncertainties associated with that information. Okay? So you'll see a red line showing what we think it is, and then a band of sort of color representing the uncertainty either side. It's also averaged, so it's a 40-year average, so it's sort of smoothed out so you don't have big dramatic signals. But this is what we see. Okay? So this is sort of 1600, 1200, 800, and you can see the average sea ice. So this isn't summer, this is the average between summer and winter. And these are our observations of what is happening today. This is a really dramatic change. This is not something we've seen anything like for the last 1,000 years. If we want to go back to a time when we're really sort of thinking about the ice-free conditions that we might be expecting, then we need to go back probably 6,000 years before there was sort of significantly less ice than there was today. Okay? So it really is a very dramatic change, and it's really the speed of that change which is a problem for wildlife around the Arctic. Okay, so let's look at this more carefully. So I wanted to update it because a lot of these graphs have 2012, but we did have another year in between. And the nice thing is that in 2013 it bounced back a bit, which is really good news for us, because when I taught this class last year, in winter of 2013, 2012 was the last data point, and it just looked like it was heading straight down. Okay, so the nice thing was for us is that weather makes a difference. Year on year, we see different weather patterns. It was slightly cooler this year. We had different wind patterns, not as big storms, and so we were able to hold on to more of that sea ice. But it's probably not going to keep bouncing back up. We are still likely to see a continuing decline. Okay, but it's not perhaps quite as worrying as it was last year. If we look in comparison at January, so in the middle of winter, okay, and this even has 2014 on, because it's now February, then we can see that we are still seeing a decline in the winter extent of our sea ice, but it's not nearly as dramatic, because it's always going to be cold in the Arctic Ocean. Okay, so even if we melt away all our summer sea ice, we're still going to have a certain amount of sea ice in the winter in the Arctic, because it is a very, very cold place to be. Okay. So instead of just looking at month by month, what we tend to plot with these things is that sort of annual path of the sea ice. And definitely in your quiz this week, I'm going to get you to look at the most recent image, which is sort of updated daily, and you can see how much sea ice we have. And you can really see how dramatic that loss was in 2012 compared to anything we'd seen before. And no one heard about it. I was horrified by this. In 2013, you can see it's following more the pattern of, say, 2010 and 2011, which is reassuring for us. We would like that to continue. Okay. So, looking at those numbers, in September of 2012, how much sea ice did we have compared to the September average between 79 and 2000? So read those numbers off for the September in 2012 compared to that average, which is the black line. What percentage did we have? And that's most people. Any last answers? Okay. So let's take a look, see if everyone can do math today. 70% if you can, at least. Okay. Yeah, so if we look in September, the blue line shows about 4 million square kilometers. If we look at that black line, it's showing more about 8 million square kilometers. Okay? And I know you're really young, so I'm going to show how old I am now, because I was born in 82, which is just after that 1979. So that means that in my lifetime, from when I was born to today, we have lost half of our summer sea ice. Okay, and I'm really not that old, okay, I promise. So it's a really dramatic change. If you speak to your parents, they would say the same thing. And what we're sort of falling into the trap of is this shifting baseline. This is the same thing that we see in a lot of environmental problems, is that we don't think back to what was normal when our parents were kids. We think back to what the world was like when we were kids. And this is the same thing that's happening in, say, fisheries, where our fishes are getting smaller and smaller and smaller, and we don't notice it because it's not that bad compared to when we were kids, but if we compare it back further generations, it's a really big change. Okay, so this is a really dramatic change. Unsurprisingly, if we are losing sea ice extent, we are losing sea ice volume. Okay, so as well as just shrinking that area, we're also shrinking the thickness of that sea ice. And especially this year, yes, that sea ice extent bounced back, and we see a little corresponding increase in our sea ice volume, but not to the same extent. Because really what we're doing by increasing that sea ice extent for just this year is we're really just creating that 1 year ice that will melt again. We're not creating this multi-year ice that's going to hang around for any sort of length of time. Okay? So with our volume, we can definitely see that we're also increasing pretty quickly. Okay, so do you remember this image? And this shows you the movement of water around the Arctic Ocean. We've got the Beaufort Gyre, we've got the transpolar drift that brings sort of the current across and down. Okay? And this is pretty important if we want to think about the thickness of our ice and the age of our ice. So I'm going to show you a little video. And with your neighbours, I want you to do a few things for me. So I'll show it a couple of times because it's a pretty quick little video. I want you to look at the sea ice and see if you can see the patterns, like that gyre and that transpolar drift in the circulation of that ice. Where the multi-year ice is, how do we lose it? Where does it go? And what has been happening to the overall amount of that multi-year ice in the Arctic? And also, therefore, think about if we're losing this multi-year thick ice, what implications does that have for, say, our sea ice extent and volume in the future, in the summer? Okay? So let me find our little video. So this is my video here, and I wanted to introduce it briefly. The darker blue colors, I'm going to turn the lights down again a little bit. The darker blue colors are that first year sea ice. The whiter the color, the older it is, okay? So that sort of white stuff is probably sort of 5-6 year old sea ice that's been around for a while. So I want you to watch it circulate, and this is going between 1987 and I think 2012. So keep an eye on it, and I'll play it a couple of times. Bit of a change, huh? Okay, so now think about those 4 questions. So think about which features of that Arctic Ocean circulation can you recognize? Where is that multi-year ice, that white ice? Where is it going? How are we losing it? And how much do we have at the beginning compared to the end, okay? And what implication might that have, okay? So speak to your neighbors. I'm going to ask you for your answers, okay? Okay, so what features did you spot? Which of those sort of circulation features did you spot? No one spotted any? I don't believe you. I saw everyone doing this.
Yeah, that.
Sorry?
A gyre.
The gyre, absolutely. Did you see how it was moving in a circular way, right? So let's go back to my little diagram for a second. So if we look back at my circulation plot, okay, so it's slightly sort of sideways compared to where you're watching it, but that thick ice was piling up against the Arctic coast of Canada, right? And then it was sort of being moved in a rough circle around. And then where was it ending up? What was the other thing that you spotted? Yeah, absolutely. We had this transpolar drift, and that's where if we got that old ice into that current, it just headed straight down into the Atlantic, right? It went really quite fast across there, and that's really how we lose that multi-year ice. If it's been circulating around the Beaufort Gyre, it can last for quite a while, but as soon as it gets into that transpolar drift, it's gone. Okay, and so that's really where we lose our Arctic sea ice. It's down that sort of coast of Greenland, sort of spills over and flows down. So how much multi-year ice did we have at the end compared to the beginning?
Much less.
Not a lot, right? And especially those big melting years of 2007 and 2012 destroyed a lot of that multi-year ice. And so if we look at, say, the balance of what was present in the winter, we still had sea ice over a large area of the Arctic Ocean, but it was no longer that nice old sea ice, those sort of paler colors. It was that blue ice that's pretty sort of that first year ice, okay? So how easy do you think it is going to be to melt back the ice now compared to in the past? So if more of our Arctic is now covered with this thin first-year ice, how easy is it going to be to melt it back? It's going to be easier, right? If we had much of the Arctic filled with thick multi-year ice, then even if we had a certain amount of melting, at the end of the summer, there was still a certain amount left, okay? Whereas if a lot more of our Arctic Ocean is now filled with that first-year thin sea ice, then we can melt it back really quickly as well. And so once we hit that point where most of our Arctic is filled with this thin first-year ice, each year it becomes easier and easier to melt it away. And that's what we are seeing happening today. Okay, so this is what we've seen. These are the patterns, and this is taken from your UN Global Outlook for Ice and Snow. And it shows the difference in the age of the sea ice, which is related to its thickness, between 1988, which remember is even more recently, and 2005. And you can see just how quickly that old ice, that 6 to 10 year ice, is just vanishing from our Arctic Ocean. And this shows the same thing. It basically shows that that white 5-year-old plus ice is diminishing, and at the same time, we're therefore growing the amount of that first year thin sea ice that's easier to melt back in our summers. Okay, so we're really dramatically changing. It's not just the extent and the volume, it's really what makes up our sea ice up there. Okay, so the question is are we close to a tipping point? And so you might have heard this idea when we've talked about climate before, this idea that there are tipping points. And really all this means is that if we increase temperature, then the sea ice doesn't respond linearly. It means that at a certain point, it dramatically changes. So for example, if we take our graph here, say it's temperature along the bottom. If we increase our temperature, then initially whatever is responding to it is changing gradually. But at a certain critical temperature, all of a sudden there's a really big jump, okay? And then after that jump, it's pretty stable again. So this is the question: are we going to shift from a climate state when there's pretty much sea ice in our summer to really, really quickly a state when sea ice is not present in our summer? And it's because of these positive feedbacks, the fact that as we keep melting more of our old ice, we get more of this first year ice, which is again much easier to melt back again in the summer, and it's a positive loop going on. Okay, so are we close to a tipping point? So these are a whole bunch of squiggles, which is what you get when you run climate models. Okay, and so this is very up to date. This is a paper, this was research published last year, 2013, showing what a lot of the models predict for how much sea ice we'll have in the coming decades. And in the top panel, we have our RCP 4.5, which is sort of a middling one. And then at the bottom, we have our 8.5, which is our worst case scenario, where we just burn everything, basically. Okay? And this stretches from 1980, 2012 is marked on there, and so this is sort of 2100. Okay? So it doesn't look good in general for sea ice. With our medium case scenario, then our sort of average of our sea ice models has the extent being sort of around 2 million square kilometers or so. And that's a pretty soon change as well. It's going to be there by maybe 2060. If we go with our worst case sort of scenario, which is what we're tracking right now, then we could see potentially sea ice-free Arctic by 2040 with our most extreme model, but certainly a sea ice-free Arctic in the summer by 2070. That's not that far away. You guys are going to see 2070. And so this is something that's happening within your lifetime, and your children won't necessarily sort of know of sea ice in the summer. Okay. And that's what it looks like on a map, which I think is more powerful often. So that's where that blue shows what it would have been in 1970, and that sort of pink shows where that sea ice in the summer could potentially be by 2100. And remember, this isn't winter sea ice. There's still going to be pretty extensive winter sea ice, but summer sea ice is really what we're concerned about. So let's think about the consequences of that. And I'm going to turn the lights back up so you don't all fall asleep. So we have these amazing polar ecosystems that are so wonderfully adapted. We heard about this on Wednesday, so wonderfully adapted for sea ice. And they're very specialized, and there's relatively little diversity. And so what's going to happen is that sea ice declines. Well, fairly obviously, those really specialized creatures aren't going to do so well, okay, for a number of reasons that we'll talk about. If we want to think about the total amount of biological activity that happens in the Arctic Ocean, that might actually increase. If we can expose that ocean water to sunlight rather than capping it off with sea ice, then we might actually get more of that productivity, more of that photosynthesis happening, and especially if we're warming our waters as well, then we could actually see an increase in that productivity. But that ecosystem's no longer going to be its unique ice-dependent Arctic ecosystem. Instead, it's going to be basically an extension of our Atlantic or our Pacific ecosystems. Okay, so the main problem is it's no longer going to be its unique self. And the question really that we have, and we don't necessarily know the answer to this, is how adaptable are our plants and our animals going to be to this change? Okay, and that's an ongoing question, and lots of fights in that about in the science literature. But we can say some things for certain, which is in the next 100 years or so, both at the top of the food chain and the base of the food chain, we're going to see changes to what things are eating, okay? Because our ice algae is likely to disappear, our seals won't be able to use the sea ice anymore. There's going to be increased competition from things from the Atlantic Pacific moving north into the Arctic and potentially outcompeting our polar species. Increased predation rates. If you're stuck on land rather than nice floating sea ice, then you're potentially more vulnerable to attack. Also, things like killer whales and orcas might be more successful. Increased risks of disease and parasites. If you're now cramming all of your seals closer together in the same area compared to spreading them out onto larger areas of sea ice, then they're going to be exposed to more disease, more parasites. Greater exposure to pollutants, especially if people are around, and just an increase in human traffic and impacts on the environment in any case. So these are the things that our polar ecosystems and our animals are going to have to deal with, and the question is how they do that. And it doesn't just affect our ecosystems, it really does affect us in a number of interesting economic ways. So first of all is fisheries. If we're messing up our polar ecosystems quite as much as we predict, then we're of course going to see changes in the patterns of the timing of that initial primary productivity. We're going to see changes in sort of what those fish are eating, where they're migrating, how they're migrating, when they're migrating. And so all of these things for the fisheries industry up there are really unknowns. They're really uncertain, and they're interested to see what will happen. It potentially may increase some fish stocks, it may decrease others. It's a very, very complex problem. We already mentioned this idea that our sea ice forms an ice lid on the ocean, and so it can moderate the effect of waves and storms, and so it prevents erosion. And this is especially a problem where we have permafrost thawing at the same time, is that now we don't have our sea ice anymore, we have more wave action at the coasts, and we can get a lot more erosion. And this is a real problem for a lot of the communities that live around the Arctic, because really most of them do live along coastal areas, and so the erosion is happening incredibly rapidly in some of those places. New shipping routes. So if you look at the current route that you need to take if you're going to go from Tokyo around to, say, Rotterdam and European ports, you have to come all the way through past India, up through the Suez Canal off the coast of Somalia, where all that piracy is going on. Whereas if we don't have sea ice, you can pop across the top. Okay? You potentially save 40% of your shipping time, shipping costs. And that's a really significant saving, okay, if you can easily do this. The same thing happens if we think about the Northwest Passage, which people died going in search of in the last 100 years or so because it wasn't there. But if we look at, say, if you want to go from San Francisco to Rotterdam, you have to come down through the Panama Canal, and instead you could go up through the Northwest Passage. It's less of a saving, but it's important. And this is pretty important for Panama. And it would be very important for Egypt as well, because these canals generate a huge amount of their income. You have to pay to travel through those canals. They're thinking about building another canal, I think slightly further north of Panama, because it's a big business. These tankers are just enormous. Okay? But there is concern, therefore, about the pollution that would result from this. What would you do if you had a massive oil spill up there? How would you clean that up, especially given that your water is covered by sea ice for much of the year, given that your ecosystem is so delicate already and already under all of these pressures? But there's a lot of money involved here, and people are not messing around, especially on the coast of Russia, where already you can see an open shipping route that people have started using. And this is the amount of days that you would be able to travel that, sort of predicted for the future. So in 2000, probably I would look at the 50% line. Most ships would be able to cope with that. In 2000, maybe sort of 25 days of that year or so were capable of being sort of traversed along that sort of Russian coastline. By 2100, it's going to be over 100 days a year. So it's a much more sensible proposition to do this. And so it's a really interesting question, really, which company is going to make the most of this, because you might need sort of ships that are designed slightly differently for that. Energy. This is where the big money is. Billions and billions and billions of dollars. And this is where the next gold rush is, basically, along the top of Russia there. The Arctic produces 10% of our world's oil and 25% of our gas. And probably 25%, so a quarter of our estimated sort of undiscovered reserves are in the Arctic Ocean. And as we start using up some of our other reserves, this is going to become much more economically sort of valuable and much more likely to be exploited. And so, as an example, ExxonMobil recently agreed to invest $500 billion, it's just crazy money, in developing offshore reserves with Russia there. So this is big, big money, big deal. But it's a still very challenging environment to work in. And the US has banned exploitation of oil currently in its Arctic areas because it says that the companies haven't provided enough safeguards to prevent oil spills, and they haven't sort of provided any guidance as to how they would deal with it if, and realistically when, it happens. And so that's sort of a big question. How are we going to sort of balance these factors? Because the question is, who owns it? So if we go to Antarctica, we have a nice treaty in Antarctica. We have certain countries that own certain sectors, and we have a treaty that excludes things like mining. It's preserved for science, it's preserved for the ecosystems, okay? But who owns the Arctic? A lot of people claim they own the Arctic. Who actually owns the Arctic? It's a really interesting question, and right now it's being fought over a lot more so consistently, because if we look, if you're within 200 miles of a coastline of, say, Russia or Canada, then you're in their waters. If they find oil down there and they can exploit it, it's theirs, okay? But if you can demonstrate that your seabed is geologically part of your country, I'm not quite sure how they do that, but you can then lay claim to it. And so you have Russia going and planting their flag on the sea floor going, this is mine, okay? Just like we did when we were sort of, give me 2 more minutes, what are you doing? Got plenty of time yet. Okay, so the question really is, how do we balance our human activities with the environmental concerns up there? It's all very well to have this gold rush and this amazing opportunity, but what is that really going to do? So, let's have a look. I need the people at the front to be my honesty people. A lot of the ice is melted in here. Have we seen any change? No. A lot of my ice is melted here and made a mess. Have we seen a change? Yes. So, does melting sea ice affect sea level? No. Give me 1 more minute, guys. I know you're done, but any more answers? Okay. So our answer is no. Okay. Even those of you that still think it's yes. No, because it's floating already. Okay, I'll see you Monday.